Hello. Today we're looking at trapezoids and kites. Well, we'll start with trapezoids. You might already know what a trapezoid is. Then again, if you don't feel bad. They don't come up very often. In fact, I can't remember the last time I used the word trapezoid in a sentence outside of a math class. But you need to know what they are. It's a quadrilateral with one pair of opposite sides that are parallel. So it's not a parallelogram because the other sides are not parallel. And in fact, the other sides are called legs. The parallel sides are called bases. As you can see, it's not a very restricted type of polygon. All the sides don't have to be congruent. In fact, none of them need to be congruent. The angles don't have any particular relationship in an ordinary trapezoid, except that they do have to add up to 360, because a trapezoid is still a quadrilateral. The isosceles trapezoid, well, that's a little more interesting because there's more things we can say about it. Why is it an isosceles trapezoid? Well, much like the triangle, the legs, remember, iso means equal, celes means legs, equal legs. The legs here are congruent. And the bases, of course, are still parallel. That has to be true, or it's not a trapezoid. These legs don't have to be congruent, but for an isosceles trapezoid, they do. And for no particular reason, I superimposed a triangle over this isosceles trapezoid. And it's kind of easy to see that if you take a triangle and cut it, it doesn't have to be a midsegment. It can be any segment adjoining two sides. If you do it such a way that this side is parallel to this, for instance, if this were a midsegment, we'd already know that this midsegment was parallel to the opposite side here, and we'd have a trapezoid automatically. We can create one always by joining the midsegment. In fact, if we do it right in such a way that this segment is parallel to this one, we can draw a line anywhere along here, from this leg to this leg, and create a trapezoid. The only condition is that this has to be parallel to this. What if we had, this happens to be an isosceles triangle, and when you do this with an isosceles triangle, you're going to end up creating an isosceles trapezoid. If this was not an isosceles triangle, it would still work. You could still cut it with a line horizontal to this and end up with a trapezoid. So if it helps at all, think of a trapezoid as a triangle with top part, say, cut off. If I pull this away, what do we got? We got the trapezoid where it was just cut off. And just like with an isosceles triangle, isosceles trapezoid, these are called base angles. Let me double check that. Yeah, a pair of base angles would be this angle, and then this angle, and this angle. Why? Because this is a base, this is a base, this is a leg, and this is a leg. So trapezoid has two bases, two legs. Well, these pairs in an isosceles trapezoid are congruent. What else can we say about it? Well, actually, you can say a lot of things about an isosceles trapezoid. And here's a few theorems with things we can say about an isosceles trapezoid. As I pointed out, the base angles are congruent. Conversely, if a pair of base angles are congruent, then we have an isosceles trapezoid, just like with the old isosceles triangle. with an isosceles triangle, the base angles had to be congruent. On the other hand, if we found congruent base angles, we knew we had an isosceles triangle. Well, same thing for trapezoids. And here, it's isosceles, and there's really no analogy with triangles here. Triangles don't have diagonals. The diagonals are congruent if it's isosceles. On the other hand, if the diagonals are congruent, then it must be isosceles. That's the if and only if part right here. This is the only one that might seem, well, it shouldn't be too big a surprise after all. If this is isosceles, then this length is exactly the same as this. So when I go from here to here, which is going along this base, and then I'm going back this way some distance. Well, if I go from here to here, that's like going along this base and then back this way. I admit I'm talking about the long route, but they're identical, and these angles are identical. That's not really a proof. It's just an indication that it makes sense that these two paths from here to here and from here to here would be congruent. It's very sensible. Of course, the fact that it makes sense doesn't mean that it's true, and it's certainly not a proof. To see why the diagonals would be congruent here, all we have to do, let's take a look at this one here. We just break it up into two triangles, ABD, there we go, ABD, and ACD. I colored them in here. I didn't color in this line. I guess I could, because it's part of both. So it would have to be both green and blue, whatever color that turns out to be. Well, if I can show that this triangle is congruent to this triangle, and that these two are the corresponding parts, these are the diagonal. So if those are the corresponding parts of congruent triangles, they're congruent, and we're done. So, are these two triangles congruent? There's this one here, which has this angle. On the other hand, there's this one here, which contains this angle. That's A over here and D over here, and they're congruent because it's isosceles and the base angles are congruent. Okay. It's an isosceles, so we know that this side is congruent to this side. And actually, in these triangles, they're sides. In the trapezoids, they're the legs of the trapezoid. Now, AD is AD. It's congruent to itself. So, side angle side tells us that these two triangles are congruent. Now, we already know this corresponds to this. This side corresponds to this side, and all that's left is for AC, that's this, is congruent to BD, which is the other diagonal. And we're done. Once again, we just had to break up our polygon, or find a way to break up our polygon into congruent triangles, and then use the old fact that corresponding parts of congruent triangles are congruent. And this last little fact about a trapezoid is not that easy to prove, and I'm not sure the proof is all that instructive when it comes to trying to remember it. Maybe the easiest way to look at it, and what this theorem here is saying, they're telling us that pretty much like with a triangle, if we connect the midsegments of a trapezoid, and it doesn't have to be an isosceles trapezoid, any old trapezoid, the midsegment will be parallel to the base. Well, that makes sense, because I've drawn a trapezoid Maybe I should change the color of this. So all I did was create a trapezoid by cutting off the top part of a triangle. And you can always make a trapezoid that way. Just draw a line, parallel. Now in this case I drew a midsegment. Why not? This is the midsegment of the triangle. Now we know that if we draw another midsegment up here, we'll have a line parallel to this. And why was that? Well, that was because if we draw a line, in other words, we draw the altitude from here to here, the midsegment will cut that altitude in half, just as it will cut these in half. Remember, if we cut a triangle here, aside from being parallel, it's also 1/2 of AB. Well, you could think of this as 1/2 of the average of AB and this, but this is 0. So we've got the average of this length and this length, which comes to a point right here, and a point has a length of 0. Now up here, we haven't come to a point yet. If we just consider the trapezoidal part, forget this top half now. Well, is that yeah, it's a half. Forget the top part. Then we could continue the analogy and take the average of this and this, because this doesn't have 0 length. And that turns out to be right. So one way to remember this, since you already know the Midsegment theorem for triangles, which says that it's half the base and parallel, or I should say half the other side. You draw the midsegment from one side of the triangle to the other. It's parallel to the third side and half the length of the third side. Why? Well, because the top part has a length of 0. If we cut it, if we were to draw a line off here and then cut that in half, now we have to include this distance here to figure out what the length of this is. Before it was the average of this and 0. Now it's the average of this and, well, we can call that CD. As we go up the line here, you can see that CD, if we just always call it CD and run this line up, as it gets shorter and shorter, it becomes 0. And that makes sense because when we get to a triangle, we drop the average and just take 1/2 of the opposite side. If it doesn't come to a point where the upper part is 0, but we have another parallel line on top, then we have to take the average of the two. And that, of course, is only true for midsegments. There is a way to figure out the length of, say, a third segment. If we went a third of the way up here and then drew a line, there is a way to figure out what that would be in terms of AB and CD. But they're not asking us to figure that out. And we'll wait and see if any of the problems ask us to do that. They probably won't. So if this helps you remember it, fine. If not, I guess you can just memorize it. That works too. But if you cut it with a midsegment, a trapezoid, you'll end up with a line that's parallel to the two bases, and the length is the average of the two bases. Also, we have to take a look at something called a kite. You're probably familiar with kites, the kind that you fly. Now this is different. I mean, the kite you fly, I've seen them in all kinds of shapes. I've seen cool ones that look like dragons flying in the air. Well, this doesn't look anything like a dragon. This is a particular shape, and it has a mathematical definition. Pretty simple. The old parallelogram was that pairs of opposite sides are congruent. Now what we have is a quadrilateral with pairs of adjacent sides that are congruent. In other words, and another way to look at that is, if you took two triangles, and they'd have to be isosceles triangles for it to be a kite, you could draw one here, and then one here, and you've got a kite. So it's like two isosceles triangles put together. So is there anything stopping this side from being congruent to this side? Well, no. But if you did that, you'd have a rhombus, wouldn't you? Because all the sides would be congruent. So, a rhombus is also a special case of a kite, isn't it? There's a couple of things to know about a kite. Number one, its diagonals are perpendicular. And that kind of makes sense if you think of this as two isosceles triangles put together. The angle bisector is perpendicular in an isosceles triangle, and in fact it coincides with the segment bisector. In other words, the angle bisector bisects the opposite side in an isosceles triangle. Well, being a perpendicular bisector of this means by definition it's perpendicular to this line right here, which would form one side for this isosceles triangle and one side for this isosceles triangle. It also happens to be a diagonal, and it's perpendicular to this, which is also a diagonal. So remember, the diagonals in a kite have to be perpendicular. Also, one pair, this pair of angles has to be congruent. It's getting a little messy here. These two don't have to be. In fact, they aren't. It might look kind of close, but notice that this has to be a much wider angle than this one. Notice how the end of this triangle is much farther away than this one. If you think of these as two triangles, this isosceles triangle is much longer than this isosceles triangle. So these two opposite pairs, they are not congruent. If they were, we'd have a rhombus, I think. We definitely have a parallelogram if that happened. For a kite, only these two. So we've got one pair of congruent angles, and the diagonals are perpendicular. Well, now that we're experts on trapezoids and kites, let's work some problems here. Find the length of the midsegment. Well, they didn't even have to tell us it was a midsegment because they've drawn these little hash marks here. This side's congruent to this side, so this must be a midpoint. This segment's congruent to this segment. I should have said this segment's congruent to this segment. And same thing over here, so this is the midpoint. Connect up the midpoints, and you have, by definition, a midsegment. What is the length of this? It's the average of the two bases. Real easy. 21 plus 25 over 2. That's 46 over 2, I think. You probably did that one in your head, didn't you? Now let's see here. Which one of these is not always true? The base angles of an isosceles triangle are congruent. That's true. Always. As long as it's isosceles. The midsegment of a trapezoid, it doesn't matter what kind of trapezoid it is parallel to the bases. That's always true. The bases of a trapezoid are parallel. Well, yes, that's part of the definition of a trapezoid. The legs of a trapezoid are congruent. No. That's the definition of an isosceles trapezoid. Not a regular one. Any old regular trapezoid, you can't say for sure, that the legs are congruent. So the correct answer is D, of course. Well, okay. It looks like my buddies Inseam and Fleabite are still trying to work out geometry problems. That's a good thing they're politicians. That way they can't do any real damage. There's a couple of things wrong with what they did here. One pair of opposite angles in a kite are congruent. I think he picked the wrong pair. For one thing, usually you can just look at it and see that it's the long angles that aren't going to be congruent. These two are. Why? Well, because look at the angles these come together at. This is a pretty sharp angle. This is a pretty wide angle. On the other hand, over here, they look about the same. But there's another way you can look at this. This is still a quadrilateral. The angles still have to add up to 360. So if this were 50, and this is 120, for instance, he's saying opposite angles, that would be both pairs of opposite angles. So that's 240. And 50 and 50 is 100. 240 is this angle plus this angle here. And that's going to be 340. Well, that doesn't look like 360 to me. Matter of fact, this actually has to be 70 degrees. These two are congruent. They have to add up to 360, so. Now, our mission here is to find the lengths of each side of the kite. And they're giving us the lengths not only of the diagonals, but of these sections of the diagonals. Makes it even easier, doesn't it? Because we know this is a kite. Maybe I should put that in there so we know it's a kite. There. Now, we know it's a kite. Kite diagonals intersect at 90-degree angles. Well, we have a right angle. More than that, it looks like a isosceles right triangle. So we can just instantly write square root of 2 times 3. Remember that? For isosceles triangles, we studied the 45-degree, that's isosceles, and the 30-60. Well, this is isosceles, so it's root 2 times the square root of 3, and root 2 times the square root of, root 2 times 3, and root 2 times 3. Forget square root of 3, it's got nothing to do with anything, pardon me. Square root of 2 times 3, that's what these two sides are. Now these we're going to do about the same way. Unfortunately, we don't have a 3, 4, 5 triangle here. We got a 3, 5 something else. So we're going to have to actually maybe do some computations here. 3 squared is 9. 5 squared is 25. And the square root of that will give us y. See, remember that's Pythagoras' theorem. This squared plus this squared equals this squared. We take the square root. And this is the square root of 34. Too bad. That was the square root of 36. We'd be almost done, wouldn't we? Well, 34 is 2 times 17. There's just no squares we can pull out, is there? So you could grab your calculator and get a number for this. It's probably 5.8 something. Or just leave it as square root of 34. I think most anybody would accept this as a legitimate answer. And there we go. We've got the whole thing. All we needed was Pythagoras' theorem, and we had to remember that diagonals for a kite are perpendicular. Uh-oh. Here we go again. I wish Inseam and Fleabite would just stick to politics. They always get it wrong when they try geometry. What do they do here? Well, let's see. We've got one base is 14. We don't know what the other base is. And by the way, this kind of looks like a right angle. That's okay. There's nothing that says that you can't have a right angle in a trapezoid. So don't let that bother you. This still isn't a right triangle because we've got this little side right here. In this case, it's the base of a trapezoid. But we still have a quadrilateral. It's just, if we extended this and this, we'd almost have a triangle. But that's not what we have. We know that this is a midsegment because there are little hash marks here to tell us that this is the midpoint, and this is the midpoint. We connect them up, and that's a midsegment. Well, what do we know about the length of a midsegment? We know that, let's call this length that we're looking for a y, just because it's easier to write. 8 equals the average of this and this, which is 14 plus y over 2. Now, what they should have done was written out the equation correctly, which is that AB plus DC divided by 2 will give us the length of the midsegment. So we just write it out. 8 equals 14 plus y over 2. And that leads us to y equals 2. Well, this one's not too bad. They ask us to graph the points that they've given us here. And then, just like back in grade school, you connect the dots. Except this time, we don't get a horse. We get a trapezoid. And they want us to take a look at the diagonals and decide what that tells us about this trapezoid. Well, there's only one thing that the diagonals can tell you about a trapezoid. Pardon me. If they're congruent, it's an isosceles trapezoid. If they're not congruent, then it's not an isosceles trapezoid. They ask you to actually find MP and NQ. You don't have to work it all the way out and get actual numbers for these two diagonals to know whether they're equal or not. But the problem says find the actual value, so we'll do it that way. And how would we do that? What's the distance from here to here? We got this diagonal. I'll just draw a dotted line down to the... What's this distance here? Well, we just use our distance formula. It's easy. So, MP, is that right? Yeah. We also change in y, which is 5 minus a minus 1. These two lines are parallel. So, for both of these, delta y is going to be 6. It's pretty easy to see that the distance from this line to this line is 6 units. That's the change in the y coordinates. It's going to be the same for both of them. So 5 minus a minus 1 is 6. We can just write that in. The other one's not quite so obvious. We got minus 3 minus 3. Well, that's minus 6 squared. And of course we have to take the square root of that. Well, that's 36 plus 36, right? The negative sign is irrelevant. It's the negative 6 that we're squaring. That's still just 36, so we get the square root of 2 times 36 here. And that's a square root of 2 times 6. Okay, that's one of them. What about the other one? Yeah, it's basically the same thing. Delta y, the change in y, 5 minus a minus 1. That's not going to change. As I said, these are two parallel lines, so delta y is going to be the same for both. And that's going to be 6 squared. We can just call it 36, I guess. Plus the change in x, which goes from minus 1 to minus 5. And that's 4 units, right? Heck, you can just count them if you wanted to. 1, 2, 3, 4. Wait a minute. 1, 2, 3, 4. Yeah. So it's minus 1, minus 1. Minus 5, which is the same as minus 1 plus 5. So that's 4, and 4 squared is 16. And of course we'll need the square root of that. Well, 36 and 16 is 52. Well, that's just 4 times 13, right? We can pull out the 4 and write 2 times the square root of 13. So over here we've got 2 times, pardon me, we've got the square root of 2 times 6. Here we have 2 times the square root of 13. That's for this one. Now, do these answers make sense? Well, I think it's easy to see that since the change in y is exactly the same for both of these lines, the longer one is going to be the one with the greater change in x. That's the larger number over here. So is the square root of 2 times 6 more or less than 2 times the square root of 13? It's not immediately obvious to me. So I used my calculator to get numbers I could compare and make sure that these answers make sense. Root 2 times 6 is about 8.5, whereas 2 times the square root of 13, that's about 7.2. That means this is slightly shorter than this, which makes sense. That's what we should have found. So this was actually fairly easy. I probably made it longer than it needed to be. You just have to check out the diagonals, see if their lengths are equal. If they're congruent, then we have an isosceles trapezoid. If not, we don't. And that's about the only thing we could say about a trapezoid and its diagonals. Now here's one where we have to use our midsegment for trapezoids theorem again. This one is 24, they say. And all we know about the bases is that one is 3 times the size of the other. So I really don't think I drew this to scale. I don't think this is 3 times that. But this is x, this is 3x. Now what do we know about midsegments? We know that the midsegment, the length of the midsegment, which we know is 24, is equal to 1/2, or 1/2 of the sum of the lengths of the two bases, which is the same as saying the average of the two bases. X plus 3x is 4x. 24 equals 2x. And that would imply that x equals 12. So this is length 12. This is length 36. And that would give a midsegment of 24. Okay, here they're telling us that we've got a trapezoid. I went ahead and drew it here. The PQ is parallel to RS. Okay. MN is the midsegment. They're also telling us that this bottom base here is equal to 5 times PQ. And what they want to know is, what's the ratio of Mn, that's this one, to Rs? Sounds complicated, but maybe not. What is Rs? It's 5 times, I'm going to replace PQ. Let's write it this way so you don't forget. I'm just going to call it X from here on, okay? It'll save you writing a whole bunch of PQs. What do I know? If I call this X, then this here is 5X. And this is something else. What is the ratio of Mn to Sr? I wonder if we could work it out all at once. We put Mn on the top. I'm going to do it like this. Mn over Sr. Well, this could be a long expression up here on top. Let's see what it is. It'll be X plus 5X over 2. That's the length of our midsegment, right? The average of these two. And what's this? This is 5X. Guess I shouldn't have drawn this line so long. I'll have to go down here. That's 6X over 2, which is 3X. And that's 5X. The x's cancel. And I get 3 to 5. Let's see what we got here. 3 to 1, 2 to 1, 5 to 3. Well, that's pretty close. Oh, here we go. 3 to 5 right there. That's all you had to do. You could have actually worked out Mn first and then tried to figure out what the ratio was. It seemed easier to just write out the ratio and then replace, our substitution rule for equality. Replace Mn with what it is. Replace Sr with what it is. Putting them both in terms of X, of course, that way they can drop out, and we've got it. Well, that's about it.